Okay, ladies and gentlemen, let's continue with Chapter 8. Chapter 8 is Internal Forced Convection, and today we're going to do the last paragraph, which is paragraph 8.6, Turbulent Flow in Tubes. We've already looked at the average velocities, the average temperatures, the laminar region, how the flow develops, and we've looked at the section on 8.5, laminar flow in tubes. So, as I've said, let's continue with paragraph 8.6, turbulent flow in tubes. Okay, we know that in tubes specifically, the critical Reynolds number, where the flow changes from laminar to turbulent flow, is at approximately 2,300. Okay. If experiments is conducted of the Nusselt number as a function of Reynolds number, then at 2,300, the Nusselt number, or let me rather do it like this, sorry. The Nusselt numbers typically, yeah, it is actually, does something like that. Okay. So it increases a little bit in the laminar flow regime as a function of Reynolds number, depending if there is secondary flow or not. But that we will do in the next chapter. So in the most ideal cases, if the flow is laminar and fully developed, then the Nusselt number would stay constant, either 4.66 if it's a constant heat flux, or 3.66 if the wall temperature is constant. Okay, up to this point where the gradient changes, and then after that there's a linear increase again. So if you go and look at it very carefully, you will see that up to about a Reynolds number of 10,000 and even more than that, maybe 30,000, only after that, the increase in Nusselt number as a function of Reynolds number is quite linear. But in this region, after transition, things are not so linear as it should be. And therefore, it is very difficult to get good equations for it. So, in this specific paragraph, it is considered as if the Reynolds number in Reynolds numbers in most cases is larger than 10,000. So, most of the correlations are valid only if the Reynolds number is larger than 10,000, and there are many of them who are only valid even at larger Reynolds number, 30,000 and even more than that. Okay. Now the heat transfer coefficients, or the Nusselt numbers, which we're going to get from the Nusselt numbers, the Nusselt numbers is we're going to get from equations that were developed from experiments. Lots of experiments and empirical equations which were curve fitted through all these equations. Okay, now before we get to the Nusselt number, equations for turbulent flow in tubes, something that we're going to use in many cases is the friction factor. So let's just go back to the friction factor, and the first equation which is given in the textbook is the equation of Petterkoff, specifically for a smooth tube. Okay, and for a smooth tube, the friction factor is equal to 0.790 multiplied by the ln of the Reynolds minus 1.64 minus to the minus 2. And this equation is valid for Reynolds number larger than 3,000 and smaller than 5 million. Okay. Now, with this in mind, we're going to get to the first equation which can be used for turbulent flow in tubes, which is one of the oldest ones, which is known as the Chilton-Colburn equation. Chilton-Colburn. And this equation gives the Nusselt number as 0.125 multiplied by the friction factor multiplied by the Reynolds number multiplied by Prandtl to the third. Okay. So for us to get the Nusselt number, you can see we need the friction factor. And the Petikov equation is but one of many equations that can be used to get the friction factor from. Okay. A simpler version of that one is the equation 0.184 Reynolds to the minus 0.2. Okay. Some of them more accurate than others, but there are quite a lot of equations which are available in your textbook that you can consider to be used. Okay. Now if we do this and put this into here, then the so-called Colburn equation was developed, and the Colburn equation looks like this. The Nusselt number is equal to 0.023 multiplied by the Reynolds number 0.8 to the Prandtl to the third, which is valid for Prandtl numbers larger than 0.7 and smaller than 160, and for Reynolds numbers larger than 10,000. And following this equation is the so-called Dittus-Boelter equation. The Dittus-Boelter equation, which gives the Nusselt number as 0.023 Reynolds to the n, Reynolds to the 0.8, Prandtl to the n. Prandtl to the n, where n is equal to 0.4 for heating, if we do heating of the tube, and it is 0.3 if we do cooling of the tube. Okay, and that is not the end. After that was developed the so-called Cedar and Tate equation. Cedar and Tate equation. And this equation is specifically where we have large variations in properties. Large property variations. Okay, and this equation gives the Nusselt number as 0.027 multiplied by Reynolds to the 0.8, Prandtl to the third, multiplied by the viscosity of the bulk at the bulk temperature, divided by the viscosity on the surface to the 0.14. And this equation is also valid in a certain Reynolds number range and a certain Prandtl number range. Okay. The details are in your textbook. Okay. So the details are given there. Okay. Okay, now what is large property variations? When do you use this equation and when do you use the other equations? This equation specifically, remember, we spoke about that previously. This is, if this is the tube, that is the viscosity at the bulk temperature. Okay, while this would be the viscosity on the surface. Okay. Now, if that ratio to the 0.14 is significant, then you've got a large property variation. And there's no guideline for it. You have to choose yourself. If it is 0.9, is it 0.8, is it 0.7 or whatever. Okay. So the choice is yours. Now, you might find it a little bit shocking, but most of these Nusselt numbers have errors of plus or minus 25%. Plus or minus 25%. And there are two reasons for that. The first reason is this original work and the original experiments were conducted more than 50 years ago. And they didn't have the modern instrumentation that we have today. I mean, temperatures at that stage were not measured with thermocouples, and they didn't have Coriolis mass flow meters today available that we have today that can measure mass flow rates up to with errors of less than 0.2%. So they did the best that they can, but it's not only that. What is important to remember is that with all these equations, the Nusselt number, because it is forced convection, is a function of the Reynolds number and the Prandtl number. Okay, now the Reynolds number, as we know, is equal to rho, the velocity, multiplied by the diameter, divided by the viscosity. The Prandtl is equal to Cp, mu, and K. Okay. And then there are lots of temperature measurements to get the heat transfer rate. And to get the heat transfer rate, you have to measure the mass flow rate, the Cp, and the delta T's. Okay. Now, if you really have a very, very state-of-the-art laboratory like we do, then you can measure temperature differences up to 0.1 degrees Celsius at best. Okay. They couldn't do it 50 years ago. Now, again, you must remember that with every one of these measurements, there's an error. And you multiply these errors all with each other. Okay, so it's small errors, but all of them together causes quite a large uncertainty. And that is the reason why the Nusselt number errors are plus or minus 25%. Okay. Well, they did try to do a little bit better. And Petkov then derived a more accurate equation. I'm not going to write it down, but it was then followed by Glinski from Germany, from Karlsruhe University in Germany. And his equation looks like this. The Nusselt number is equal to the friction factor divided by 8 multiplied by the Reynolds number minus 1000 multiplied by the Prandtl number divided by 1.07 plus 12.7 multiplied by the friction factor divided by 8 to the power of 0.5 multiplied by Prandtl to the 2/3 minus 1. Okay. And the equation is valid for Prandtl numbers larger than 0.5, smaller than 2000, Reynolds numbers larger than, take note, 10 to the 4th, and smaller than 10 to the 6th. Okay. Okay, and it was claimed and expected that this equation might be accurate to plus or minus 10%. But again, Glinski used all the same data than the previous researchers before him. Okay, what is also important with turbulent flow, which is different than with laminar flow, is that constant heat flux and constant surface temperature doesn't matter now anymore. Okay, so the correlations are not a function of is it a constant heat flux or a surface temperature. Okay. So they are not sensitive for different, let's call it, boundary conditions. With laminar flow, it is very, very important. With turbulent flow, it is not the case. Okay. Now, I have a very good student with the name of Nicole Bateman, and over the past 5 years, we've been working on this equation to see if we can actually develop a better equation, and we did. Okay. And this equation, which hasn't been published yet, which we hope to publish this year, looks like this. It says the Nusselt number is equal to pi divided by 70 multiplied by the friction factor multiplied by Reynolds to the 1.11 multiplied by Prandtl to the third. And that equation is definitely accurate to plus or minus 10%, or within the band of plus or minus 10%. In terms of the Reynolds number range, it is valid for Reynolds numbers larger than 10,000 and smaller than 5 million. 5 million. The Prandtl number range, 0.1 to smaller than 10. So we haven't done experiments yet with oil or something like that so that we can check the equation at higher Prandtl numbers. So at this stage you can just take note of the equation. You will see it is much easier to work with than this one, much simpler and less calculations. Then in your textbook there is also an equation for liquid metals. Okay, for liquid metals. Why is liquid metals so different? Because the Prandtl numbers are very, very small. Typically in this range, and there are one or two equations that you can use for that. These equations has been developed for a round circular tube. Now the question is, what happens if the tube is not round? Okay. Fortunately, for non-circular tubes, we use the hydraulic diameter. We use the hydraulic diameter, and it gives a good estimate. Okay, it's not exactly, but it gives a good estimate. Okay. Tubes that you're going to use quite a lot is to look at cases where you have flow through an annulus. Okay. So you might have flow through the inner tube, but the flow you would like to consider is in the annulus, and there are actually quite a few students who are busy with designs, not under my supervision, but with other people, where they are considering that, where they want to know what is the heat transfer in an annulus. Okay, so that is the annulus, and the hydraulic diameter for an annulus is very easy. It is just equal to the difference in the two diameters. Okay, so that is equal to di, and that is equal to d0. And together with that, in your textbook is given a table 8.4, and it gives for different diameter ratios the different Nusselt numbers. Okay. Now the difference between the two different Nusselt numbers is it depends if it's on this wall or on that wall. Okay. So in table 8.4, limited information is given on flow through an annulus. If you would like more information, then Dr. Jaco Dirker, he was also one of my undergraduate students, and he did his master's and his PhD under my supervision, and he developed quite a few correlations for the flow through an annulus. So if you go and look in the literature for Dirker and Meyer, then you can look at the years 2002, 2003, 2004 and 5. Okay, and then the most recent one, we have a few master's degree students who are also working on this, because it's actually very complicated. I'm not going to go into the details now, but Van Zyl, Dirker and Meyer, and it was published very recently, 2013, and you can go and get all the correlations there, or all the graphs, if you would like, prefer to use that. Okay. In essence, what you will see is that the Nusselt number is now a function of the Annulus ratio, as well as the Reynolds number, as well as the Prandtl number. So you can go and get the correlations there. Okay. Something else which is of practical interest is heat transfer enhancement. Heat transfer enhancement. Heat transfer enhancement is where on the inner surface of the tube the geometry is changed for two reasons. Okay. First reason is to give more surface area. Second reason is to make the flow more turbulent. Okay. In this case, this can, for example, be microfin tubes. Typically, a tube with a diameter of 10 millimeters will have 80 of these fins on the inside, and they are spiraled, okay, like that of a gun barrel. So they are spiraled on the inside, so that the flow doesn't only flow through in that direction, but the flow is also spinned through the tube. Okay, it's heat transfer enhancement, and there are also equations available for that. Not in your textbook, but in literature. Okay. And another type is a fin which more looks like that. Usually a little bit larger types of fins. Again, it increases the surface area and it increases the turbulence through the tube. Okay, to make things more clear, let's do an example. This example, it looks like the example in the textbook, but I've changed it significantly. Okay. So this example is of flow with an inlet temperature of 20 degrees Celsius and with a volume flow rate of 50 liters per minute. So you've got this long tube. The tube is being heated with an electrical resistance element. The tube length is 5 meters. The tube diameter is 30 millimeters. And the outlet temperature is 80 degrees Celsius. And they ask us to determine the power rating and the surface temperature at X equal L at the outlet. Okay, it's water. Inlet temperature of 20 degrees Celsius, the volume flow rate 50 liters per minute, the length of the tube 5 meters, outlet temperature is 80 degrees Celsius, and the question is determine the power rating and the surface temperature at the outlet of the tube, at the exit. Okay, you all understand the problem? Okay. What is a good bulk temperature? Good bulk temperature would be 20 plus 80 divided by 2 is 50 degrees Celsius. 20 plus 80 divided by 2, 50 degrees Celsius. And at 50 degrees Celsius for water, you can go and look at table A9, where you can get the properties of the water. And the properties are, the density is equal to 988.1 kilograms per cubic meters. K is equal to 0.644 watts per meter Kelvin. The dynamic viscosity is equal to 0.547 multiplied by 10 to the minus 6 square meters per second. And Cp is equal to 4181 joules per kilogram Kelvin. And the Reynolds number is equal to 3.55. Okay, let's calculate the mass flow rate through the tube. The mass flow rate is equal to rho multiplied by the volume flow rate. Remember that V, like this, is equal to the volume flow rate in cubic meters per second. So that is equal to 988.1 multiplied by the volume flow rate. 50 liters is equal to 0.050 cubic meters, and it is per minute, so divided by 60, and that gives us a mass flow rate of 0.8317 kilograms per second. The heat transfer rate is equal to the mass flow rate multiplied by Cp multiplied by the outlet temperature minus the inlet temperature. Okay. The mass flow rate we have just calculated is equal to 0.8317. Cp is equal to 4181. And the temperature difference is 80. The outlet temperature minus the inlet temperature is equal to 20. And that gives us a heat transfer rate of 208,682. Okay. That is not an engineering answer. Okay. That is equal to 208.7 kilowatts. Okay, that's the first part of the question. Determine the power rating, 208 kilowatts of heat, electrical energy which is being converted into heat energy. Okay, let's calculate the second part. That means we will have to go and get the Nusselt number so that we can get the heat transfer coefficient here. To get that, we need the Reynolds number. To get the Reynolds number, we need the velocity. Okay. The mass flow rate is equal to rho AV, the average velocity. The mass flow rate is equal to 0.8317. It's equal to the density. The density is equal to 988.1 multiplied by the cross-sectional area. It's pi divided by 4. Multiplied by the diameter of the tube, which is equal to 30 millimeters, multiplied by the average velocity, from which we can solve that the average velocity is equal to 1.179 meters per second. Any questions? Great. Reynolds number, the average velocity multiplied by the diameter divided by the kinematic viscosity. The average velocity is equal to 1.179 multiplied by the diameter divided by the kinematic viscosity, which is equal to 0.547 multiplied by 10 to the minus 6, and that is equal to 35297. Okay. 35297, and the result is that we can say, well, before we do that, let's first calculate LH and LT. The flow is turbulent, so it would take 10 diameters before the flow is fully developed. 10 diameters, which would be equal to 0.3 meters. Okay. 0.3 meters. So in terms of the length of our tube, which is 5 meters, .3 meters would be approximately there. In the beginning, the flow would be developing. After that, it would be a constant. Okay. Therefore, we can say that for this case, we can assume it's fully developed. Okay. And we also know that we don't have to assume it, but we know the flow is also turbulent. Turbulent flow. Okay. We can see that from the Reynolds number. The Reynolds number for a smooth tube where the flow changes from laminar to turbulent flow is approximately 2,300. It's more than 10 times larger than that. Okay, now Nusselt number is equal to 0.023 Reynolds to the 0.8 Prandtl to the 0.4, and I've chosen the Dittus-Boelter equation. The Dittus-Boelter equation. Okay. Why? There are 5 or 6 equations that you can choose from, and what I'm going to tell you now is very, very important. Okay. A lot in this course we work with empirical equations, and with any one of those empirical equations there's always a fine print. Okay. So where in the textbook you see the equation, you have to go and read when and where the equation is valid. And it would be a good investment for you to use a red pen or something like that and to go and highlight that for you. So every time when you go back and you choose an equation or you're going to look at an equation, you have to look at when and where is it valid. Now the situation is for turbulent flow, lots of equations are given. They start with the historical, the oldest equations, and then move back to the latest ones. But except for that, there's not very good guidelines. Okay. And in the test and an exam, you're going to be under pressure. So you can choose an easy equation, or you can choose the Glinsky equation, which is a more difficult equation. It takes longer to calculate, and the chances of making a mistake is larger. Okay. And if you are as lazy as I am, then you also prefer to use the simplest equation, that one. And that's the only reason I've chosen that equation. Okay. So we are going to use this equation, but then we are also going to look at some of the other equations and see what is the influence on the results. Okay. So let's choose the Dittus-Boelter equation equal to 0.023. The Reynolds number is 35,297 to the 0.8. The Prandtl number is equal to 3.55 to the 0.4. And that gives us a Nusselt number of 217.9. The Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity. The Nusselt number we have derived now is 217.9 is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity, which is equal to 0.644, from which we can solve the heat transfer coefficient as 4,343 watts per square meter degree Celsius. 4343. Heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the surface temperature minus the mean temperature. The heat transfer rate is equal to 208,682 is equal to the heat transfer coefficient is equal to 4343. The surface area is pi multiplied by the diameter multiplied by the length multiplied by the surface temperature minus the mean temperature is now going to be, we want to know what is happening here. That is the surface temperature. The mean temperature is going to be the exit temperature, which is 80. Okay? And the result is that we can solve the surface temperature as 164.9 degrees Celsius. Okay. Now before we can look at one of the more modern equations, we need to calculate the friction factor. So the friction factor, I've given you two equations that you can use to calculate it with. 0.790 multiplied by the ln of the Reynolds number minus 1.64 to the power of minus 2. If you calculate the friction factor with that equation, it is equal to 0.02273. And if you've calculated it with the other equation, which is simpler, 0.184 multiplied by the Reynolds to the minus 0.2, then the result is equal to 0.02266. So we can see it's very, very close in any case. I would always recommend to you, ladies and gentlemen, when you calculate the friction factor, remember you've got a Moody chart in the back of your textbook. Okay. So why do I tell you that? Well, just go and check at the Reynolds number. At that Reynolds number, go and check on the Moody chart and make sure you get about the right friction factor. Just to make sure you didn't make a calculation error. Okay. Now, according to the Glinsky equation, the Glinsky equation gives the Nusselt number as the friction factor divided by 8 multiplied by the Reynolds minus 1,000 Prandtl divided by 1 plus 12.7 times multiplied by the friction factor divided by 8 to the power of 0.5 multiplied by Prandtl to the 2/3 minus 1. Okay. And I'm too lazy to go and write down all these values. You can go and do that at home. Okay. If you go and do the calculations, then you'll get the Nusselt number as equal to 243.8. 243.8. Compare it with 217.9 of the Dittus-Boelter equation. You can see it is plus or minus 10 or 20%. Okay. Okay. Now, if you've got this Nusselt number, you can go and recalculate the heat transfer coefficient, and you can go and recalculate the surface temperature. And the result, if you use that, then the surface temperature is 171.1 degrees Celsius. Previously, we've estimated 165. Now it is 171 with the Glinsky equation. Okay, the new equation, if you use the new equation that I've given you, the Nusselt number is equal to pi divided by 70 multiplied by the friction factor multiplied by the Reynolds number 1.11 Prandtl to the third. If you use this, then you can calculate the Nusselt number as 218.1. 218.1, and from there the surface temperature as 181.9 degrees Celsius. Okay, so the three different equations giving temperatures of 175, 171 and 182 degrees Celsius. Okay. Ladies and gentlemen, any questions? Nothing? Thank you very much.